Okay, this is problem 3 from the worksheet. And you are given this Cartesian equation, and the first thing you're asked to do is to graph the thing. Now, one way to do this is to plot some points. This is a plane, so just 3 points will determine that plane. There's another way to look at this. I'm going to set one of these variables equal to y, and the one I'm going to use is x2. This doesn't change anything except the fact now that I'm going to plot y vertically, so the y value will be rise, and these two will be run. Solving for y, we're going to get y is equal to 3x1 plus 2x3 minus 7. So when we're plotting, we're going to look at this, and now you can tell what this is. The slope in the x1 direction, the pitch, is 3. And the yaw, the rise over the run in the x3 direction is 2. And the intercept is minus 7. So using my Amazon provided plane, here it is. We begin with a horizontal plane. The pitch is 3. So the pitch is x1 in that direction. Yaw is 2. Intercept is minus 7. That's the plane right down there. You see that? There it is. Okay. So we'll try to draw a picture of that. But now you can get a pretty good handle on what that graph is going to look like. I'll put the x1 direction here, the x3 direction here, the x2 or the y direction there. So it goes through the point minus 7 down here. It's pitched pretty steeply in the x1 direction and fairly steeply in the x2 direction as well. So something like this. So this is how to get a handle on what these graphs look like without really doing much. Let's take a look at the second part. So here now we want to list some points. So use the equation to list points on the graph. Now for plane, points are always a good idea. If you can get to the point where you can compute points on the graph, you will be able to find everything that you want. So if there are shortcuts, maybe there are shorter ways to do it, but finding points on the graph always will get you any of these equations. So let's take a look. Let's take a point on the graph. There are some easy ones. Let's see, if x1 is 1 and x2 is 2, then the y value will be 0. 3 plus 4 is 7 minus 7 is 0. If x1 is 0, and let's say x2 is 4, I've got these backwards. x3 is 2, and x2 is 0. x1, x2, x3. So now if x1 is 0 and x3 is 4, 0 and 8 minus, so we get a 1 there. And now if x3 is 0 and x1 is 3, 9 minus 7 is 2. So here are a bunch of points, but we can do a lot of them. If x1 is 1 and x3 is 1, then x2 is, or y is minus 2. So if we label these points A, B, C, D, then we can use those to determine directions. So the vector from A to B, beginning at A and ending at B, 0 minus 1, 1 minus 0, 4 minus 2, and then C to A or A to C, 3 minus 1, 2 minus 0, 0 minus 2. And we can get a couple more directions here. B to C, 3, 1, minus 4. Maybe A to D. All of these are vectors in the direction of plane. So 0, minus 2, and minus 1. So here are directions of the plane. Four or five directions, list of points. Part D, find two parametric equations that have Alfred as their range. By the way, this guy's named, the plot of this thing is Alfred. And so now for a parametric, the parametric form, we will want a point on and two directions. So we've got a lot of choices here. For the first choice, the point on, might as well pick A, 1, 0, 2. And for the direction 1, we could pick minus 1, 1, 2. And direction 2, 2, 2, minus 2. We want to make sure that these directions are linearly independent. They are. They're not multiples of each other. There are only two of them. And this will give us the equation for this plane. I'll call it P1. P1 of T, S and T, is equal to the point 1, 0, 2 plus T times minus 1, 1, 2 plus S times 2, 2, 2. And S and T can be any real numbers. They are free variables. So there is parametric form 1. I asked for a second one. What I had in mind, what I wanted to show you is that these can look completely different, these equations, and still give you the exact same range. So I'm going to erase the gold and replace it by something else. And then we'll get P2. Let's see, maybe we use blue. So now the point on, let's use 3, 2, 0. Got a lot of different choices. And we'll use these two directions, 0, minus 2, minus 1. And maybe 3, 1, minus 4. So now using those, we can, I'm going to erase a little bit of this. I'll put P2 up here. Parametric form 2. And this is really a function. Probably should have called it a function. So P2 of S and T is equal to the point on, 3, 2, 0, plus S times the first direction, 0, minus 2, minus 1, plus T times the second direction, 3, 1, minus 4. So here are the two different parametric equations. S and T are free variables in both of them. The idea is that these things have a lot in common. Their range is exactly the same. It's exactly the same plane, but they look completely different. But since S and T are free variables, if you plug in all possible S and T's here, you get that plane. The plane with x1 slope 3 and x2 slope 2 with intercept -7. And if you use S and T's here, you get the same plane. Okay. And finally, find the equation of a line that is orthogonal to Alfred. Now, I didn't ask you for the point normal form. We could have gotten that. But we want the normal line, a perpendicular line. And I'm going to leave these parametric equations up. So I'd like a normal vector. And, this normal vector will enable me to get the parametric equation for the normal line. Now, I've actually erased the original equation. I'm going to put that up in a minute to show you maybe a faster way to do this. But since we have these two directions, for example, these two directions are in the direction of the plane, your a normal vector, one normal vector, is simply their cross product. 0 minus 2 minus 1, cross product with 3, 1 minus 4. Or an alternative, you could take minus 1, 1, 2, direction 1 from the gold, cross product with 2, 2, 2. Both of these vectors will be normal to the plane. There sort of is only one direction normal to the plane, but these will have the same direction but be of different lengths. So you can compute these cross products, and both of those will work. Either of them will work. And let me get a parametric equation for that normal line now. Parametric function for the normal line, or the perpendicular line, or the orthogonal line. So to do this, this line, L of t, will need a point on, and we'll need just one direction. Well, since we ask for any normal line, we can take any point. This doesn't have to be on the plane. This line will intersect the plane, but the point we take for the line does not have to be in the plane. And the direction is one of these lines, n, whichever one you want to choose. And then the line will be 0, 0, 0, in this case, plus t times this n. And if you chose a point that's on the plane, that's fine. There's no problem. But since I asked you for the normal line, you don't actually need that. So this line is perpendicular to the plane. And that's it. So that's it for problem number 3. That completes it. But there is something else I wanted to show you that has to do with how to get another way to get this n. I'm going to write up the original equation again. 3x1 minus x2 plus 2x3 equals 7. And I'm just going to manipulate this a little bit. 3x1 minus x2. I'm going to put a minus 7 here, bringing this plus 2x3 equals 0. And now I'm going to write this as a dot product. 3 minus 1, 2, dot product. So those are these coefficients, 3, minus 1, and 2. And writing this as a dot product, this will be an x1 here, In the second instance, we'll get a x2 plus 7, because when we multiply it by the -1, we'll get minus x2 minus 7, and that's what we've got here. And then a 2, then an x3. Now this dot product is 0. So this tells you two things. 3 minus 1, 2 dot x1 minus 0, x2 minus a minus 7, x3 minus 0 equals 0. Just putting in a little bit of arithmetic here. This tells you two things. It tells you that the point 0 minus 7, 0 is on the plane. And this tells you that the vector 3 minus 1, 2 is perpendicular to the plane. So here is a vector form for, here's a vector equation for that plane right here. And you can get it from the Cartesian equation, from the normal Cartesian equation, simply by doing a little factoring out using the dot product. Here's a Cartesian equation for the plane. Here's another Cartesian equation for the plane, but it is a vector equation using vector operations and vector notation. And here you get the point normal form for the plane. So you can get this directly without taking the cross product. That's it for problem 3. I'll put problem 4 up in a minute. And